This is AI Podcast, and today we're digging into a new paper called AnalogCoder from AI 2025.
Mm-hmm. The one where an AI basically writes code to design analog circuits. Give me the quick version first.
TLDR, AnalogCoder uses a large language model to write Python that builds and simulates analog circuits, checks whether they meet specs, and then fixes its own mistakes in a loop. No special model training, just smart prompting and a simulator in the loop.
So it's like a very diligent intern who keeps running experiments, reading the error messages, and trying again until the test passes.
Exactly, and on a fairly broad benchmark, it solved most of the task and beat a strong general-purpose baseline.
Who's behind it?
Lead author Yao Lai with collaborators across the University of Hong Kong and UT Austin. You'll recognize David Z. Pan on the author list as well.
Nice, let's back up. Why is analog design such a headache in the first place?
Right. So digital circuits are mostly ones and zeros, which makes them predictable and easy to verify at scale. Analog circuits live in the messy real world. You're choosing a topology, setting device sizes, and balancing gain, bandwidth, noise, power, and stability. Tiny tweaks can push the whole thing off a cliff.
And the data problem is huge too. We don't have giant labeled datasets of good analog schematics the way we do for language or images.
Exactly. Plus the space is continuous and nonlinear. A small resistor change can make a simulation blow up or refuse to converge.
Okay, what did people try before this?
A mix of approaches. Reinforcement learning to place devices step by step. Graph models trained on curated circuit datasets. And lately a few LLM-based systems that can spit out spice code. But the limitations were real. Many needed fine-tuning on domain data. Some only tackled topology or sizing, but not the whole loop. And most lacked a robust repair cycle when the first try failed.
Got it. So AnalogCoder's pitch is, don't train a domain model at all. Treat design like programming with tests.
That's the core idea. The agent writes Python that calls into a circuit API, generates a netlist, runs SPICE-style simulations, reads the results or error traces, and then rewrites the code to fix issues. Think of it like test-driven development for circuits.
Can you walk me through a toy example?
Sure. Say the task is a common source amplifier with a minimum gain and a bandwidth target. AnalogCoder drafts code to instantiate a transistor, a load, and biasing elements, runs an AC analysis, and checks the results against a test bench. If the gain is low, it revises device sizes or the bias network. If the simulator says singular matrix, it realizes a node isn't properly referenced and adds a resistor to ground. It keeps iterating until the test bench says pass.
And there's something about a skill library too, right?
Yeah, that's clever. When it discovers a working subcircuit, say a current mirror or a source follower, it saves that pattern. Later, for a more complex task, it can pull from that library instead of reinventing the wheel. That reuse mirrors how human analog designers work.
What about the prompts? Are they just please make an amplifier or more structured?
More structured. The prompts nudge the model to produce runnable, well-commented code, to interpret simulation logs, and to propose at least one concrete fix per failure. The authors also emphasize asking the model to explain why it made a change, which helps keep the repair loop grounded.
Let's talk experiments. How did they evaluate this without turning it into a cherry-picked demo?
They assembled a benchmark of a couple dozen analog design tasks spanning basic building blocks up through small composite circuits. Each task ships with a test bench that defines pass or fail. They compared AnalogCoder across a range of large language models and tracked two simple metrics: how many tasks were solved and the success rate when you allow multiple attempts.
What tools were under the hood?
Python with a SPICE backend, so the loop is literally code generation, simulation, inspection, and repair. No private data required.
And the headline results?
The system solved 20 out of 24 tasks and beat a strong baseline by about 5 tasks, all without any fine-tuning. The authors attribute the gains to the feedback-driven repair and the reuse of those saved subcircuits.
That's impressive for training free. But I'm wondering about reproducibility. If you swap the underlying language model, do you get different outcomes?
That's a fair concern. Performance does depend on the backbone model, and closed APIs can drift. The paper reports numbers for several models, and the codebase is designed to rerun the benchmark, but you'll still see some variance due to sampling. Setting seeds and documenting prompts helps, but it's not perfect.
Another question. Do they handle sizing to hit multiple specs under corners, like gain, noise, and phase margin across process and temperature?
Not fully. The benchmark focuses on functional pass-fail under nominal conditions. It's a great first step, but real tape-out requires multi-objective sizing and PVT corners, sometimes Monte Carlo, and eventually layout-aware checks. Those are beyond the scope here.
Right. No one ships silicon off a perfect schematic alone. What about layout?
Out of scope. The system stops at schematics and simulation. Integrating with open analog layout tools would be a natural but non-trivial next step.
And dataset breadth? 24 tasks is solid, but analog is huge.
Exactly. It's a start, not the finish line. More task diversity like precision references, oscillators with strict startup criteria, or low-noise op-amps, and standardized corner suites would pressure test generalization.
I like that the paper stays grounded in an engineer's workflow. It's not pretending the model understands physics. It's pairing the model with a simulator that does.
That's the key insight. Use the LLM for hypothesis generation and code scaffolding, then let circuit math and test benches be the judge. It's like having a junior engineer who writes experiments quickly and a lab that immediately tells you what actually works.
If you were extending this, what would you try next?
3 things. First, unify topology and sizing with explicit multi-objective targets and corner analysis. Second, bring richer feedback into the loop, waveform images, stability margins, maybe even formal checks, so the agent can diagnose deeper issues. Third, aim for an end-to-end flow that goes from requirement to schematic to layout with parasitic-aware verification.
I'd add one more. Repeat the study with a strong open model and fully pinned settings. That would help the community replicate results without relying on a commercial API that might change.
Totally, and expanding the public benchmark would let everyone compare apples to apples.
All right, quick takeaway for listeners heading into the lab after this.
Treat analog design like code with tests. Let an LLM write the glue code, call a simulator, and repair itself. Even without training a special model, that loop can get you surprisingly far.
And stay realistic about the gaps. Corners, sizing trade-offs, and layout still need attention. But this shows a promising path for automating the early, tedious parts of analog design.
Exactly. It's a strong baseline and a practical template you can try today if you've got a simulator handy.
That's our show. This was AI Podcast. I'm Maya.
I'm Ethan. Thanks for listening, and we'll see you next time.